Second in a series of events that aim to question, broaden, and reframe the way we think about computing and design. I am David Benjamin. I teach here at the School of Architecture, and I'm also the co-director of the Living Architecture Lab. And we're very happy to be presenting tonight's event alongside the Department of Computer Science at Columbia in what we hope will become a deeper partnership over time between the schools. Of course, collaboration between architecture and computer science is nothing new. There's a long history of it. There's also a long history, it seems to me, of architects adopting technologies from computer science relatively late in their development cycle. So in other words, today's new thing in architecture is often yesterday's innovation or tool from computer science. So one of the things we want to explore tonight is this. If parametric, the term parametric, is today's buzzword, what might tomorrow's buzzwords be? Can we anticipate them? Can we absorb them early in their development cycles? Can we also challenge them? And can we really understand them beyond a superficial level in order to make them more than buzzwords? Can we reach a point ultimately where architects and computer scientists work together to co-evolve the tools and the designs that apply those tools, where each one exerts forces and friction on the other and both get better in the process? In order to explore this, we could not have a more interesting and inspiring group of speakers. And the basic premise for tonight is for each speaker, to demo a method or technology that might be relevant to how we will be designing architecture 10 years from now. Before we move on and get right to the speakers, I do want to thank a couple of sponsors whose support helped to make this event possible. Blue Sky Studios, the Columbia Department of Computer Science, and Bentley Systems Incorporated, particularly Laura Meyer, Academic Director of North America. And now what I want to do is quickly introduce my friend and colleague Michael Reed, the co-moderator of the event. Michael teaches in Columbia Computer Science. He is Senior Research Associate at Blue Sky Studios. And for the past several years, he's been an important friend for the school, being involved with the development of several classes here. Michael Reed.
Thank you very much, David, and good evening, everyone. Thank you very much for coming tonight. And thanks again to Bentley, the graphics group at Columbia Computer Science, and especially to the Graduate School of Architecture for providing the platform for this series, allowing us some time to reflect and to look forward on the relationship between computer science and architecture. For me, the promise of this relationship is visible in the sophistication of projects that increasingly use the design geometry itself as a program for automated fabrication and construction. But no relationship is perfect, and there are plenty of missed opportunities on both sides. The example that I usually use is John Fraser's groundbreaking work in the late 60s and early 70s at the Architectural Association, work that certainly would have formed the basis of computer science's ideas in virtual reality and human-computer interaction, except for the fact that that work really wasn't even recognized or acknowledged in my field until very, very recently. And in the other direction, there's parametric scripting, which as a design tool became widely available in the mid-1980s in a very early release of AutoCAD. That was the first time that a designer could write an interpretable script that would generate form. It took about a decade for these ideas to percolate to individuals researching in an architectural venue, 20 years until we see sort of widespread experimentation that you all know today. If this is a form of technology transfer, I'd say that it does not have much merit to it. The worst part is that it's not just inefficient, but it seems to create a situation where practitioners are expending energy and searching for the next big thing, but only within a very, very narrow interpretation of whatever ideas were thrown over the wall. So you have a situation where people are looking for the next Voronoi diagram, a mathematically beautiful pattern they can just take It's easily scriptable. They can apply it to a design situation, but without any contribution to the art of practice. Without a deep commitment to collaboration, it's going to be very difficult to be systematically innovative. So for that reason, I hope that tonight you hear and hopefully see some things that you've never seen before, or at least some ideas that are taken much farther than you've ever thought possible, because on the CS side, and that means both in computer science research and in product development, this really is the cutting edge. So with that, before I introduce our first speaker, I'll mention that at the end of the speakers, we'll have a period where we'll have some question and answer. But in the meantime, I'll introduce our first speaker. It's Jonathan Cohen. Come on up, and if you need to plug in, plug in. Jonathan is a senior research scientist at NVIDIA, where he develops methods for applying NVIDIA's massively parallel GPUs to problems in scientific computing and real-time physical simulation. Prior to joining NVIDIA, he spent several years working in the Hollywood feature film visual effects industry, where he developed software for such films as Spider-Man 3 and The Chronicles of Narnia. This includes stints at Sony Pictures Imageworks and Rhythm and Hues. He received a Technical Academy Award in 2007 for his work in fluid simulation and visual effects. And with that, are you good to go? We're getting it.
It's just working. It's not sending.
Not yet.
Just work. It's not like that. I'm sorry.
And despite testing this just 15 minutes ago, we are having technical difficulties. We got it.
No, that's
Is
not
that
this.
you or the other?
No, that's not sending anything. I think it's my laptop, not your system. Do you want to switch to someone else first, and I'll reboot?
Yeah, we could try that if you don't think it's going to go.
I don't want to waste everyone's time.
You want to try one more click here, and then after that we can bring in.
It doesn't, well,
All right.
yeah.
Okay. In that case,
Sorry.
we're going to swap our order temporarily. Hod, would you mind starting? So if you want to introduce Hod, that'd be great, and we can figure this and get it going.
So I'll introduce Hod Lipson. Hod has been to the school before. His work has some close connections with some architectural experimentation, but I think you'll find a lot of this very fresh. So quick introduction, Hod Lipson is an associate professor of mechanical and aerospace engineering and also of computing and information science at Cornell University. He directs the computational synthesis group, which focuses on novel methods of automatic design, fabrication, and adaptation of virtual and physical machines. He has led work in areas such as evolutionary robotics, multi-material functional rapid prototyping, you've probably seen the YouTube videos of these things, machine self-replication, and programmable self-assembly. Lipson received his PhD from Israel Institute of Technology and worked as a postdoc at Brandeis University and also MIT. His research focuses primarily on biologically inspired approaches as they bring new ideas to engineering and new engineering insights into biology. Hod Lipson.
Thank you. Pleasure to be here tonight. I'd like to talk to you a little bit about a couple of projects that we're doing, but I want to focus in particular on one new idea that we've been beginning to explore and in robotics, and I think it might have implications to architecture as well. So, and that's the idea of self-reflection. So let me explain a little bit where we're coming from. So there are a lot of, I see, in the beginning, we mentioned this idea that architecture can use ideas from computer science. And I think another area which combines computer science and engineering is robotics. And there are, as far as I can see, a lot of new ideas in architecture involve various forms of robotics, in particular reactive, responsive systems that actually measure things and react to them in various ways. And this is just one picture off the web of a reactive wall, but there's many like these, and they correspond in a way to something that, a kind of era in robotics that happened maybe a decade ago, where people started designing reactive robots that didn't do too much processing, but they reacted to their environments in various ways, somewhat like insects maybe, and a lot of interesting things happened. And we've been exploring that as well. So I want to talk a little bit about the trend in robotic and where I think this is going and some of the new ideas that are coming out. So in the early days of robotics, and most robotics still today are programmed. It's just a programmer sitting down, designing the robot, and then writing a program that makes the robot do something very specific. And that works very well in a closed environment where everything is the right place and the right time, and the robot works in the factory and everything's all well. But this kind of robotics fails when things change, when there is a need for adaptation, when something is not in the right place, when the bulb falls off. In those cases, these kinds of robots, for them, it's game over. They can't adapt, they can't react, they can't recover. And so one of the biggest challenges in robotics is to try to make machines that can adapt to new and unforeseen situations. And we've been doing a lot of work on that for a while. And one of the earlier projects was to try to make robots that evolve, literally using Darwinian selection, like genetic algorithms, genetic programming, and learn over time, and their shape changes in order for them to react to new situations. And these are, I don't know if I can play these. These robots are evolved. We took a vat of robot components in simulation and bred them over 1,000 generations, and we got these simple robots that can crawl across the floor. After doing that, we started taking the same ideas and making them work not in simulation, but in reality. So we took a existing robot. This robot has 12 actuators, 12 pneumatic actuators in it. And we let it evolve in reality. So we let it basically try out lots of different controllers.
Then this one is a bit better.
It didn't do very well. You can see it's trying to learn how to walk. It's not doing that well. And gradually, from the feedback it's getting, it's learning how to walk. Basically what's happening is there are lots and lots of controllers or brains on this robot
7 liters.
Try different things, and those that can make the robot walk faster get to breathe more. We take them and we recombine them with other controllers and we produce new robots as controllers, and gradually the machine learns how to walk.
They get better and better.
It's not ready to take over the world yet, but it's definitely learning how to walk, and it's doing that without being programmed. So it's kind of a machine learning process. But here's the key challenge. So the first project, we did everything in simulation, and we downloaded it, and we crossed our fingers. We hoped that it worked. But that doesn't really scale, because there is what we call in engineering the reality gap. You can have fantastic things in simulation, but when you make them in reality, it doesn't necessarily work, because there's a gap between simulation and reality. And no matter how much time you spend on simulation, there's going to be always this gap, and it's going to be a problem. In the second project that I briefly showed you here, we did everything in reality. But the challenge there is that the robot needed to learn in reality and need to do lots of physical trials, and it took time and was very expensive. So that's a problem with too many physical trials. When you have a machine or a system and you want to have it learn in reality, just is too expensive and too slow. So the alternative, and this is the basic idea of self-reflection, which I want to put forward today, is this idea that you start off with a simulation and you use it to generate machines. And let's think about structures, not just machines. Any kind of thing you want to actually physically instantiate. And then you try it in reality. You take the best thing you have, you try it in reality. Now, because your simulation is not going to be good to begin with, probably the thing you're going to build is not going to work very well. But we're going to collect data from the robot, let's say, its experiences, its actions, and its reactions, and collect all this data. And now, instead of just evolving structures, we're going to evolve simulators. Okay, so in the first couple examples I showed you, we evolved machines. Now we're going to evolve also their simulators, where the figure of merit of a simulator is how well it explains reality in retrospect. So now we're basically co-evolving machines and their simulators, and I want to argue that that is self-reflection. When the machine actually tries to generate new simulators that explain its own experiences, that is basically a process of self-reflection. It's not that an engineer or an architect hand-coded a simulator to let the machine figure out what's going on, but the machine does it for itself. So let me show you how that works first for a simple robot, and then we'll try to see to project into the future. So this is a robot that we built. It has 4 legs. It has 8 motors, 2 on each leg, 1 at the hip and 1 at the knee. And it has 2 tilt sensors that tell the robot how it's tilted left and right, forward and backward. Okay, very, very sparse input. Now this robot needs to learn how to walk. Now the challenge is that this robot does not know that it has 4 legs. All that it knows is that it has 8 motors and it can feel the tilt angle. So imagine yourself sitting in a black box with no windows, and you have 8 knobs, and you can turn the knobs, and as you turn the knobs, you can feel the box leaning left and right, forward and backwards. And with that, you have to learn how to make the box move forward. So that's what this robot feels like, so to speak. So the way it works is that the robot begins by doing a random motion, and it then formulates hypotheses about, or models, simulators. These are hypotheses about what it might look like, and I'll show you the movie in a second. And you'll see that all the hypotheses, all the simulators that it generates for itself are wrong. But they are, insofar as the robot knows, they are all valid hypotheses because they match its experience. You will know that they're wrong because you happen to know what the robot actually looks like. It will then, and this is the key step, it will figure out what's the best action to do to cause the most disagreement between predictions of these models. Why? Because the action that it will do, the data it will collect, will then refute or rule out some of the models and leave others intact. So then we'll do a physical experiment, rule some of them out, and keep on going in a circle until it cannot disambiguate them anymore, at which point it has a good simulation of itself, and then it can make the model in simulation move forward. And because the model is pretty much correct, what makes the model move forward will make the robot move forward as well. So here's an example of this thing working. And if I had more time, I'd show you all the failures as well, but I'll skip straight to the thing that works. And this is the robot doing its first random action. And now here are all the hypotheses that it's generating. You can see they're all wrong, but it's kind of figure out that they all make the center green block tilt in the same way. This is already 8 out of 16 trials. It's beginning to figure out that it's got 4 legs. Doesn't quite know how they're hooked up and where. And this is already the 16th trial out of 16, and it basically created a model of itself. Okay, now it's not a great model. It's not very accurate. It's pretty simple, but nonetheless, making that model move forward will also make the robot move forward. We were hoping for the robot to generate some evil spidery walk, but instead created this lane. We have some sound. We have some sound back. It will make it even nice. So it has a nice clickety-clack kind of motion. So the point of this is not that this is a great way to make robots move forward. Okay, this is all about the machine creating a model of itself and then using that to fly. Okay, and just to test it, we remove the leg off the robot and watch what happens. So nothing happened. Try this again. So remove the leg. Suddenly the dynamics changed, and then it kind of internally begins to adapt its model. It basically lost the leg internally. If you look here, it didn't quite lose the leg. It just made it very short. And then, because it still has to explain where all the 8 motors are, and then it figured out a way to move forward without a leg. Again, it's not a great way of moving forward, but the basic point here is that there was no sensor that says leg in box. So we felt the materials, the machine, measured what's going on, adapted self-image, and used that self-image to figure out an alternative way of moving forward. It's all about adaptation. And if you look at how this thing behaves, red are the random models, what the random controller does. Black is what the self-model predicts, and blue is where the robot reaches in physical reality, which suggests that the self-models are, this is a robot from academia, so the self-models are inflated, but nonetheless, it allows the robot to move forward in interesting ways, which is interesting because it means that the self-model doesn't have to be accurate in order to allow the machine to move forward. It has to be good enough to allow it to make the right decisions. And you can do that with what we're working now is having a robot model another robot, like theory of mind and so forth and things like that. So you're probably by now asking yourself, okay, this is cool, but what does it have to do with architecture? This is all robotics. And I want to take a step backwards and think for a moment, okay, if we're talking about machines that can model themselves, what can we do with that? And you know, I see in architecture, there's a lot of talk now about models of buildings and green buildings that can turn off and on sensors to maintain an environment and so forth. There's a lot of modeling and simulation that has to go on, but we're still usually talking about simulation that some expert comes along, you pay him a lot of money, and they create a model of your building, and that model is probably going to be wrong a year later, right? Because everything changes. So how about thinking about buildings and things that can actually adapt and create a model of themselves? And we did one simple experiment that's somewhat close with a structure, not a building. This is a bridge I walk over when I cross when I walk to Cornell every morning. Until recently, it was more like this. And when you cross the bridge here, you have a long time to think what would happen if one of the bars would fail. And so we said, okay, let's take the same idea and apply it to a bridge. So this time we have a bridge, you can barely see it here at the top, with one element that's 10% weaker than it needs to be. Now, but this is a self-modeling bridge. So what it does, it has small vibrators various places, and these vibrators vibrate the bridge in tiny amounts, and then the bridge can sense the vibrations, and from that it can create hypotheses about what it is, where are pieces connected and how they're connected. And it forms multiple hypotheses, and then it creates new vibrations to disambiguate, to make these models disagree in their prediction, just the same way we had with the robot. And we've shown in simulation that this process, the bridge can identify the broken or the weak link a lot faster and more accurately than traditional civil engineering methods. So this is just an example how you take this idea and apply it to a structure. So we talked about self-reflective robotics, self-reflective structures. So here's the main point I want to leave you with, thinking about the future. You know, can we make self-reflective architecture that basically we have objects or buildings that act and sense and create, using that data, they create a model of themselves. They create a self-simulation, a self-image that could be of themselves, of their environment, and of their users. It's all together. Using these models, they can adapt to change faster, and we do that with fewer physical trials, just like the robot didn't have to do all these physical trials because it had the self-model. And finally, how can we take this from these simple structures and simple machines to complex things like cities? And I'll leave you with this thought. Thank you.
All right, let's see how this goes. Thanks, Hod. We're good. So once again, I'll give the short version. Jonathan Cohen, Senior Research Scientist at NVIDIA, where he develops methods for applying NVIDIA's hugely parallel GPUs to problems in scientific computing and real-time physical simulation. And with that, I'll leave it to Jonathan.
Thank you. sorry for that hiccup. I think the moral of the story is to never trust technology. So I'm going to talk about, where am I on time? Okay. I'm going to talk about throughput computing and computational graphics. So these are two sort of separate concepts, but I hope you'll come to understand why I think they're actually really interesting and relevant for people thinking about where computers are headed, and in particular design professionals who are used to thinking of computers as a tool. So the way I want to approach this idea of throughput computing is to start out by asking the question, how do you measure speed? And I'm talking about the speed of a computer. So the simplest way, and the sort of the intuitive way that you think about speed is you say, I have a task, I want to launch a render job in Lightwave or whatever it is, and I look at the clock when I start, I wait an hour and a half for it to finish, I look at the clock when I'm done, and I say, okay, that task took an hour and a half. And then a year goes by, I buy a faster computer, I run it again, and it takes 45 minutes. So, okay, it's twice as fast, right? It's a very simple, intuitive sort of way of thinking about speed. But there's another way of thinking about speed, which is maybe a little more subtle, which is the idea of, instead of looking at a single task and calculating how long that takes, is to think of throughput, which is how much can I do per second? So thinking about sort of the bulk rate at which I can do things. And so the technical term for these, the first measurement is called latency, and the second is known as throughput. And these are sort of two competing ways of thinking about how do you measure the speed of a computing device. And they lead to very different places. And so what I want to talk about today is throughput. And so if you start thinking about throughput, where does this lead you? So if your measurement is how much can I do at once, or I'm sorry, is how much can I do in a given amount of time, the sort of natural way that you would think about improving this number, right, is to do a lot of things at the same time. And so there's this inherent relationship between high throughput and parallelism. And by parallelism, I mean solving many problems simultaneously. And so if you design a processor or a computer for high throughput, the way that you would typically think about this is you'd also design it to have a very high amount of parallelism. So here's kind of a simple conceptual model. So let's say I have a glass with water and I want to drink it as fast as possible. So if all I care about is latency, the way that you might think about improving your latency at drinking this glass of water is you would buy a really gigantic straw, right? And you would suck on the straw as fast as you possibly can to slurp up all the water all at once. And if you were thinking about this in terms of throughput, you would take sort of the alternate approach, which is I'd go to the store, I'd buy a pack of 100 straws, I'd stick them all in the cup, and I'd suck through all of them at once. And this kind of illustrates the two competing ways that you would think about designing a processor, in fact. So a latency processor, it tends to be very fast, very efficient, very well designed, very expensive, very sophisticated, and very good at doing one thing really fast. And a throughput-based architecture, you have lots of little simple cores, so these sort of simple straws. And the key thing is to build something that's scalable. So I can jam more straws into this cup, right? And it'll keep getting faster and faster. And they don't interfere with each other. And you can carry the analogy too far, I guess. But you sort of get the idea. So I work at NVIDIA. There's actually lots of companies that are building processors like this. So I don't want to be like a marketing shill. NVIDIA's great, obviously. But this is in the air, and there's lots of companies that are thinking about computing in this way. And so our latest generation processor, which is called Fermi, is a great example of a throughput-based processor. And it's designed for throughput. So you might think of, you go to the store and you buy a dual-core or a quad-core CPU that has 2 or 4 cores. Well, our chip has 512 cores. And each of those cores can actually do 48 things at the same time. So in total, we can do 24,000 things at once, at the same time, on one chip. And these aren't expensive chips. This is a consumer commodity device. But the consequence of building an architecture that's designed for very high throughput is that it's really, really good at doing problems, at solving problems where throughput is the appropriate way to optimize. So math problems are a great example. You have a very large math problem to solve. In almost every case, you can chop it up into lots of smaller subproblems, solve them all in parallel. And on Fermi, for example, we can achieve over 1 trillion flops, teraflops, 1 teraflop. So that's 1 trillion floating point operations per second in single precision, and in double precision, which is more accurate math, about half of a teraflop. So you might say, well, what is a teraflop? That means nothing to me. So I want to put this in perspective. This is a chart from Top 500, which is a website that tracks the 500 fastest supercomputers around the world. And so they have some methodology where you can, there's this benchmark, you run it on your computer, and you can measure how fast it is and submit it, and they certify results. And so they've been doing this for a long time, and so this is tracking the red dots here, going back to 93, is the single fastest supercomputer in the world. And this is the logarithmic scale, so each one of these is a factor of 10. You know, it's pretty remarkable, just the steady march, right, in terms of speed, this exponential growth. And the pink dots here are the 500th fastest supercomputer in the world. So again, you know, marching pretty steadily. And so for any given year in between these two, sort of the range of the top 500 supercomputers around the world. So one Fermi chip, which you can now buy the consumer version for about $500 and the professional version next month for a few thousand, would be here. So if you look to about 2003, in 2003, this would have been the 500th fastest supercomputer in the world. So 2 points. First of all, 2003 wasn't that long ago, so that's kind of rapid progress, in my opinion. And point number two, if you actually look at the processors that make up all these supercomputers, what kind of processors are they made from? With very few exceptions, they're made from processors that are designed for low latency, not high throughput. And it's really only very recently, at the very top, these sort of more recent, the top-end supercomputers, they're starting to use these throughput-oriented processors. And so one reason that we can have one throughput-oriented processor that, you know, consumer level, inexpensive, and it can do so well, is because it's actually designed to be good at this kind of thing. You know, in the past, we took these processors that were good at low latency and then used them to solve these throughput-related problems. And suddenly, when it really is a sea change in computer science that's happening right now, is this recognition that throughput is really the way that you want to think about the speed when you're solving very large math problems. So the interesting thing, so you can go to the store and spend $500 on this literally little mini supercomputer. And the interesting question is, what can you do with it? How does this affect you, the users of these tools? So this is just kind of plotting along this axis is the amount of the processing power, so how many operations per second processors could do, and kind of representation of what kind of images you could create. So if you take all of these, the power of these processors and use it for graphics, you can make really impressive images. So in the late 90s, we had these processors that by today's standards were quite slow, and you could do these not very well tessellated polygonal models, right? About 2003, processors got fast enough that you could actually implement what's called shaders, programmable shading, so you could actually write a little program that specified the color of every point and do much more interesting effects. And we're just at the point today where you can actually do full interactive global illumination, interreflection, much more realistic and dynamic lighting models. And you can actually do them interactively on a single processor. So I'm going to show you some demos of this. So these are actual products. Come on. Please. There we go. So I know we're supposed to talk about the future. So I'm going to show you stuff that exists today, and you can extrapolate after the future. So this is, so we just released a ray tracing library called Optics, and this is a demo that we released. You can actually download from our website, called Design Garage, which is just kind of showing off as a proof of concept what you can do when you have this kind of power. So Design Garage lets you take a car model and put it in an environment and play with material parameters, and interactively it generates these images. And so you can see, we can move the camera, and it's interactive, so as you move around, the quality goes down, and then you hold still for a few seconds, and it converges to a more accurate solution. And so here's changing the skylight. And so these are the kinds of renders that people expect to take, a few hours, right, if people have played around with these high-end rendering packages. The idea that this could be interactive, I think, is kind of mind-blowing to someone who's used to running a full global illumination solution on a complicated geometric model. So these are, millions of polygons. This is showing we can actually adjust the depth of field, so simulating different focal lengths. And again, it starts out kind of, low quality, but it converges in a couple seconds to something that's actually quite good. So here we've pulled in the focus, and now back to mid-ground. So now this is showing actually editing material. So again, we can interactively change the color. We can change the specular color versus the diffuse color, shading parameters, and all the bounce light, all this stuff it's recomputed. Nothing is pre-computed. We're not reusing anything. It's restarting the calculation from scratch every time you move that slider, and it's all interactive. So this is showing a slightly different application. This is something called ambient occlusion, which is a lighting technique for getting these kind of nice soft area lights and shadows for diffuse shapes. This looks kind of like architectural models, I think. And again, showing it's interactive, so as you move, it goes to this lower quality, and as soon as you let the camera stop, within a few seconds you have a basically final quality image. And again, compare this to what you would have expected, where these are maybe 20 minutes to an hour to get an image, and here it is literally interactive. So this is showing a different technique, recent work by some of my colleagues at NVIDIA, called photon mapping, which is a different method for calculating these kind of accurate global lighting models. The point here is that there's only two light sources. So there's this light and there's this light, and everything you see is completely calculated interactively again. And so you have everything from caustics. You see the color temperature shifts as we move the lights around, and we're getting red reflection versus green reflection. As the caustic here changes and it spills more or less green light into the room, and all these really complicated effects of the relationships between light bouncing in this space. Again, totally computed interactively. So that's kind of a simple synthetic case. So let me just show a slightly more interesting case. So Morgan McGuire, who did this work, put it in a game engine. So this is kind of cool. This is a game level in a game engine that he's been developing using this lighting model. And the cool thing about it is there's only, I think there's these 3 spotlights, and that's it. So there's no synthetic cheat, ambient term everywhere, or these kind of hacks that people are used to doing in game engines. There's real lighting, there's 3 real lights, and that's it. And all of the effects of bounce light, I think there's you're right, so shining the light on the wall, and the wall's red, so you get this warm glow off of the wall, again, all interactively. And if you've ever done lighting in like a CG environment, or if you have any familiarity with it, this is just a completely different way of thinking about lighting. Game developers are not used to lighting the way the real world works. They're used to hacking it. And the idea is that as you change, when you have enough computing power, you can actually do these things accurately in a realistic way. So I want to show one more thing. This is some recent work. I think it's Alt-Enter. Yeah. So this is work that I've done recently, applying the same parallel processor, throughput-oriented processors to realistic interactive fluid simulation. So this is actually this is captured from a high-end gamer card, basically, a GTX 295. And it's actually calculating the fluid flow of air around the car. So we took this little driving game and we added this model for air flowing over the car, and added these little smoke trails behind it. And so we're actually simulating in a rather realistic way the airflow around the car. And if you think of this as a design tool, the idea now that you can have these models, and instead of sending it off to some computer-aided design package where you wait 12 hours to get a result back, this isn't accurate enough that you'd want to use this to predict real airflow. But from the perspective of getting a sense of how objects interact with their environments, these are very computationally intensive problems. But as computers get faster and faster, you can actually do more and more of this stuff interactively. And I think to a level already today that really exceeds what people expected. So this is showing we can have 3 cars and they're all interacting. And the last thing I want to show you, this is actually my favorite demo. So we took exactly the same system, but instead of driving smoke, we used a simple lift model to simulate how this would affect leaves. So we start with all these leaves on the ground, and as you drive the car around, it kicks up these leaves. Very subtle effect, but it's so realistic, the way that as the car moves around, it sort of pushes the leaves. And I think what's really cool about this is the car feels a lot more real than if we had none of this, right? If you were just driving this car around, you'd say, okay, that's not a real car. But because you feel the way the car is pushing the air, and that's pushing the leaves, and the leaves sort of fall back down, it feels like this car has weight. And the interaction of the car with the environment just really sells the idea that this is a real car, in this physical space. So from the perspective of how will you be designing in 10 years, I don't really know, but I think the idea that you will have the computational tools that will let you, in a much more realistic way, explore the relationship between your design and light and wind and air and all of these physical things that are very, very computationally intensive. I think that's really going to change the way that the capabilities people have in terms of the tools are really going to change the way that you're able to explore designs rapidly. And so that's all I had, so thank you very much.
Thank you very much, Jonathan. Great. You have a laptop? Yeah. Okay. Oh, perfect. All right, plug in. Terrific. Thank you. And for our third speaker, we have Makai Smith. Makai is the product manager for Generative Components, which many of you know is the associative parametric modeling environment from Bentley Systems. He was previously director of digital fabrication for Chrysler & Associates, an architectural composites fabricator where he oversaw pattern-making operations employing laser scanning and large-scale CNC. He practiced architecture at Venturi Scott Brown Associates in Philadelphia and holds a Master of Architecture from Arizona State University. He's taught courses in digital fabrication at the Southern California Institute of Architecture and the University of California, Berkeley, and has lectured in various schools, including the University of Pennsylvania, School of Art Institute in Chicago. He's active in the HCM SIGGRAPH and created last year's Design and Computation Gallery. So with any luck, we'll be able to connect relatively trouble-free. And there we go. All right.
Except the one.
We good?
This.
All right.
Let's see. Let me do this.
Great.
Okay, great.
All right.
Thank
I'll
you.
leave you to Makai.
Thanks. Thank you, Michael. Thanks, David, for inviting me. So I'm going to give you kind of an integrationist view on parametric modeling. So I'll speak about some practical aspects of parametric modeling. But first, I'd just like to frame this a little bit by noting that periods of flux in art and architecture are often reveal instances of what I call transitional forms. From a change in sensibility that accompanies a new technology, whether it's structural steel and plate glass, paint in tubes that let impressionists go out into the open air and paint, which helped give rise to a kind of painterly style from that, or handheld movie cameras, and finally the availability of film stock after the war to be able to shoot a bunch of stuff. And it employs, foregrounding technique, so violating the 180 rule and jump cuts, things like that. I mean, they seem almost trite through hindsight with our really jaded eyes. I mean, how many copies of a Mies skyscraper have you seen? But it's kind of a hallmark. Another characteristic is that they also don't tend to last that long in their pure form. So you have here Java Man and parametric urbanism. So if parametricism is a style that's marked by experimental uses of emerging software platforms, then my arrival at Bentley a few years ago coincides roughly with its end, because I helped to oversee the release of GC as a commercial product, so it becomes just a kind of fact of contemporary history. So in hindsight now, I know that's when you moved on to being post-parametric. But so even as the avant-garde moves on to something beyond being parametric, the diffusion of this change reveals the fact that people are more difficult than technology. Success of this enterprise is going to be predicated on architects and designers taking computational design into everyday practice. And this doesn't happen uniformly. So it's kind of captured by the Asimov wisdom, which is that the future is here already. It's just not evenly distributed. So there's an often told history of technology transfer. David made reference to it in the introduction. It's all throughout architecture in different ways. Just this example of the kind of smooth and curvy computational representations that came to architecture from engineering planes and boats. And McNeil Rhinoceros is an example of that. And so is generative components. Here, this is the work that Dr. Aish did early in his career in working in shipyards. So it's funny too, because just aside, my father was a boat builder, so I guess it should come as no surprise eventually that I come to be in the care and feeding of GC. The transfer of geometric modeling technology is not complete. We're witnessing a new round of mature solver and information modeling techniques to be adopted in architectural CAD. So the influence of MCAD, or mechanical software, it will continue unabated over the period during which parametric design will be adopted in mainstream practice. But to focus only on the aspect of how tools become more and more parametric misses the point. It's the practice dimension. That's the hang-up. So that's why I show this example from Foster & Partners Specialist Modeling Group using dimension-driven design, which is a bidirectional solver that's been in MicroStation for something like 15 years. So it's not just the presence of mature technology that's sufficient. It's deployment. This is an invitation that came to me from my alma mater, ASU, for the celebration of their 50th anniversary. And I got a chuckle because do you see the difference? Neither do I. Just the presence of computing isn't enough to transform the studio. In the past, the architectural design profession has offered up some resistance to the adoption of computation. And I mean, this could be owing somewhat to it being a humanity apart from engineering. It could also just be the result of low fees, In contrast to the traditional studio, the parametric office will be characterized by the use of computation as an intellectual or creative act, not just to produce traditional forms in a more efficient means. So it will also be characterized by a willingness to accept a role reversal into traditional design representations. So the 3D model, its related views and sections are manipulated by a generative process, and this example is from Portman. So that's the model. So the drawings themselves even are just a derivative projection from a model which is itself generated. So models like this take more time to set up, but as you know, they produce kind of change for free, kind of endless, infinite change, which is itself a kind of problem, I think. So what about drawings? Though annotation in the model will replace drawing sets as we know them now, nothing will replace the inescapable precision of locating space on a plane, because above all else, sectioning is a conceptual act. So it's primary in it, and it will stay with us over any given future look at architectural design. Post-parametric assumes that adoption is complete, that software companies have solved all the difficult problems, and it implies successful deployment of parametric technology within architecture practice at large. But architecture is quite a different circumstance than aerospace contracting and engineering. So, for example, Airbus, which helped to develop this change management or requirements management software, when it finds itself within CAD, it manifests in a different way. So now you see a graph that's being used to track the relationship among reference files, which are themselves an adaptation of CAD data storage to architectural work packaging, right? So the way that we organize our drawings and organize our thoughts. Bentley's strength in this respect comes from what seems like an overwhelming amount of really mundane software, something like 180 applications for engineering large infrastructure projects. But projects like these often have large owner-operators who hire, they're called EPCs, engineer, procure, and construct. They do a turnkey job often. So this kind of lump sum contract means the reward structure for the EPC highly motivates the adoption of data modeling and digitally integrated work processes, such as the clash detection and markup workflow that you see here, in order to manage risk. And that's why parametric design tools are more mature in the civil, plant, and structure segments, where information modeling has been in use for decades rather than architecture, which, despite our enthusiasm, is a relative newcomer to the field. So my point here is that it's not necessary to misuse software taken from entertainment or from mechanical design when such tools are being developed in parallel alongside us within the allied professions, and they just simply need to be, they need to be adapted for architectural practice, for sure. To take advantage of this requires software systems that recognize the loosely coupled, distributed, heterogeneous, and temporary nature of infrastructure projects and building projects. The approach has to be based on operational and managerial independence, geographic distribution, and incremental implementation. And this is to allow kind of emergent use, right? The pieces have to be reconfigurable in such a way that all of the uses aren't worked out at the time that they were designed. And so this is an example. It's Bentley's a solution they call it dynamic plot, but it basically allows a paper-based workflow. The interesting thing about this is that it didn't really require any new frameworks to be developed by Bentley, save for the hardware for the pen that can recognize a kind of microdot pattern. So all drawings in space are unique once plotted. So you just grab the pen, you start drawing, and it actually knows which drawing you were drawing on, and the markup shows there. And it's a kind of a good recombination of the technology. And it took advantage of the existing data and metadata that's already being used in the managed document environment. So here's another example using generative components about how we're using the platform's pieces to work with design data in a more distributed way. This is an example of passing parameters between systems. So what you have here is a city model that has attribute data, and by capturing a modeling process, that process can be based upon the input data as held on the elements. this is an approach that's different, these kind of point-to-point connections that you often see between software packages where one makes an add-in to another. It's like you might take generative components and create an add-in for it that runs simulation within the package. And these work really well for a single team that's a tightly coupled group or an individual who's working in multiple roles. But they don't scale well for the kind of long chain dependencies that work across parametric zones. So instead, we can use an approach that just looks at persisting the parametric data in the design repository and then letting each software zone interpret and consume the parametric data in its own way. So this is a feature in the kind of beta version of GC called element sensor. And I guess the takeaway about that is that it wraps both the geometry and the non-geometric data and exposes them. Another little point to make about this is that the square that you see there being moved by the cursor is just a raw element. It's just like your typical dumb geometry. And the block is a parametric component that's creating a volume based on, it's like using a logarithmic function, just measuring the area of the square to prove the point. But, you know, there's different conceptual acts here. There's tweaking, which is a non-parametric thing of just like manipulating something till it looks right. And then there are parametric components that have to respond. And so there's a role for the parametric and the non-parametric, and we have to design the system to, you know, cognitively to appreciate both. So before I conclude, I just want to call out what are probably the two counteracting tendencies here in how we might design these systems. There's gravity and centrifugal force. Gravity comes from the efficiency and computability of creating a total model. And, you know, it has to be computable. You're trying to manage it. You're trying to get it all in one place. Versus centrifugal force, because as we know, architecture, like any other creative enterprise, is a rotating body and it wants to spin itself off. There's all these different representations of a design, and they have unequal weight. They change through time and by observer, so the representations themselves are relative. And so despite the computability and efficiency of a sort of totality of a data model, the master model concept, it's just untenable. So I vote fragmented for the win. And so we'll approach this. It's very difficult to kind of manage design that way and to put it in a computable form. And so we'll have to use all of these individual techniques like parameter passing and more heroic things like search across repositories or change management systems. So this leaves me rather conveniently with only just a couple of moments to talk about the future. This is quintessentially pre-parametric. You know, it took CATIA to make the fish. But this is parametrics purely in the service of willful form making. The fish, in Geary's own words, is it's like an icon of 10,000 years. It's a pre-rational thought. But now that we've learned what the tools can do for us and incorporated them into our design thinking about, say, like continuously varying things, what happens when we've made every fish in the sea? This is Mathematica, so this stuff becomes trivial. So for one thing, I'll just make a couple of observations and then quit. So I think Joel Spolsky kind of pegged it, saying that design has to move from the user interface to the social interface. We've seen the rise of social informatics as a discipline and software that supports social networks attached to or embedded in work processes. Something like Google Apps has a twinkle of this and sort of SharePoint or something, but this stuff is just really not in architectural CAD as we know it yet. Pervasive search and access to big data that complements the social dimension together represents the full saturation of applications by the network. And this has already happened in our daily lives with mobile computing and hopefully will be followed by smart buildings. So it seems inevitable. The time scale over which this is going to happen, I think, is easy to underestimate given the way that architectural practice functions with its adoption of techniques. So, my point really is just to learn from infrastructure design because this polygon that's selected that used to be a kind of hatch pattern for a space is actually now just a geometric carrier as a place to put the description of the space on which we'll base a parametric modeling process. The period of technology transfer following from MCAD, these kind of more mature things, is going to continue for a while, I think. But it's really going to be the deployment of this stuff on construction projects and on design teams. And I think we're in a pretty good position now to learn from kind of the other professions within the allied arts. But I think for the pervasive social computing aspect, we're going to have to look somewhere else. Thank you.
Do you have the portable mic?
I don't have a portable mic.
There it is, I think.
Great. Great. Okay. Fantastic. All right, our next speaker is Eitan Grinspun. Eitan is Associate Professor of Computer Science here at Columbia University, where he directs the Computer Graphics Group, which is part of the Columbia Vision and Graphics Center. He was invited professor at the University Pierre et Marie Curie in 2009 in Paris, research scientist at the Cohen Institute of Mathematical Sciences at NYU from 2003 to 2004. He got his PhD from California Institute of Technology in 2003, and NVIDIA Fellow in 2001, Everhart Distinguished Lecturer in 2003, and has an NSF Career Award in 2007. And I'm very pleased to have Eitan speak to you today. Interactive exploration of design spaces.
Thank you so much, Michael. Is this thing working? Is the mic working? Can people hear me? Yes. Okay, because I can't hear it. So, all right, let me just dive right in. First, I want to talk to you about my field just to set things up. I work in computer graphics, and traditionally the first thing we're interested in computer graphics is the display of images. Of course, naturally we think of movies, but also computer graphics is used in preservation of artwork and in visualizing architecture. Now, what all of these images have in common is that they're stationary, they're frozen in time. And the particular area of computer graphics that I work in is the computation of motion. So if I have a scarf that's moving through the air, we can ask ourselves, how does it move, and how can we compute that motion? So what sort of questions do we need to ask ourselves? We need to ask, what sort of forces are acting on the scarf? And how are those forces propelling it forward in time? So those are some of the considerations that we're thinking about in my research lab here at Columbia. Now, when we're trying to compute the motion of a physical object, one of the things we might be interested in is having that motion predict physics, predict reality. So if we crush a can and we see this formation of patterns, these diamond patterns, we might be very interested in those. And we want to make sure that indeed, when we crush an actual can, we also get such a formation of diamond patterns. So we care about the simulation being predictive. Another, and of course, if you extrapolate from that, that leads to such applications like crash testing, virtual crash testing for cars, and so forth. Another application of computing motion is just that the process itself of figuring out how to compute the motion can teach us. For example, if we program a very simplistic model and we neglect a certain force, we neglect friction, or we neglect computation of the vortices under the wing of a flapping insect. And we're still able to get the flying motion of the insect. That teaches us that that particular physical element is not critical, or is apparently not critical to that particular motion. And so in particular, in the study of bird flight and insect flight, the act of programming a computer in order to try to mimic that motion has helped physicists to learn which forces are important and which are not important. Here's a recent example of some work we've done. In this work here, we have some honey that's poured onto a moving belt. And as the belt speed slows down, you get different patterns that form. First, you get this meandering. Then you get this chaotic region. Then you get this figure 8 pattern. And as it continues slowing down, you get more and more patterns. Here you get a coiling pattern. Now what's interesting is that in the University of Toronto, some physicists ran the same experiments but with actual honey on a moving belt. And they were able to get a lot of these patterns and in fact many other patterns. So many that this was known as the first fluid sewing machine. So simply pouring honey onto a moving belt, you get all of these sort of patterns that you expect to see in a very fancy sewing machine. And you can imagine that this has a bunch of applications, one of which is effortless decoration of cupcakes. Right? But more seriously, if you're working on electronics and you want to generate different sort of patterns of applying molten metal, which is a viscous liquid, onto a substrate, you can now look at applications where you don't have to vibrate or move the head. Just by the speed at which you move the head, you can apply different patterns onto the substrate. This is also interesting if you're interested in making flexible electronics or stretchable electronics, because now by moving the speed at which you deposit the conductor, you can get the nice zigzag that you need in there in order that when you stretch these materials, the conductor does not break. And one more area of application is baby diapers and surgical masks and AstroTurf. So what all of these have in common is that 30% of the textiles in the whole world are not the woven textiles that we're used to. 30% of them are made by this process. They're a class called non-woven textiles, and they're basically made by taking some molten polymer inside a spinning drum that has a few heads, like a shower head, that sprays out this molten stuff, and then it gets tangled up, interwoven, and then hardens. And so understanding the behavior of these molten liquids can be very interesting in terms of these manufacturing applications. I'm going to give you one more example of the sort of work we've done, and then I'm going to move on to the next topic. Similar to looking at thin, flexible fluids that are falling on a belt, you can think about looking at Twizzlers or other thin fibers, maybe human hair. So all these sort of objects that when you twist, they get these sort of interesting patterns. Our group has worked on that, and actually today, just this morning, Adobe announced the next release of Photoshop and Illustrator, CS5, and one of the new features, you can read more about it on their website, is a new physically based paintbrush that's based on this technology we developed here at Columbia, where now the new paintbrushes in Photoshop have these live dynamic physical bristles that you can paint with and get lots of interesting effects. And the same technology that went into Photoshop is also being used in a more literal sense at Weta Digital for simulation of hair. So this is the company that did Lord of the Rings and Avatar. So that's the sort of work we do in our group. It's basically taking a physical system, understanding it, figuring out what parts of it can we safely throw away, and then computing the rest of it as efficiently as possible. So how does that relate to today's topic? Well, I was asked to think about and speak about design and what that has to do with my field. And in some sense, I view design as a process of exploration. This is coming from someone who has not been educated in design, so it's a very naive, but it's my approach to thinking about it is a process of exploration. I have some set of parameters. It may be many parameters. And now I want to try to figure out within this space of parameters what are interesting, acceptable possibilities, what are not acceptable, what violates a fire code, what doesn't. And I want to explore this space. Now, typically, the space doesn't have 2 parameters. Typically, it has way too many parameters. In fact, it could have an infinite number of parameters. So we need to think of a few strategies for addressing this. I was just brainstorming this, and thought there's kind of 2 strategies you might take. One is to go parallel. If we could only figure out how to evaluate many possible designs all at the same time, right? So how might you go about going parallel in a design space exploration? One way is maybe to use parallel hardware, right? So we heard a little bit about some promising directions from that from Jonathan a little earlier. And I'd like to show you one demonstration of some very nice work done at Cornell with exactly this idea of exploring many possibilities in parallel. So here the idea is that an artist in a studio is trying to design some animation, maybe for a game. And they want to achieve a particular result. So what these blue paths that you're seeing here are many possible trajectories of this catapult that the computer has figured out, all by slightly turning the catapult in different directions, by changing the weight, by changing the force of gravity, and so on and so forth. And the user is presented, let me go back to that for a second. Right. So a whole bunch of these have been set up, and what the system offers the user now is a sort of Google for design space. So what's going on here is by drawing these red boxes, the user is narrowing down to only those trajectories that pass through the red boxes. And by drawing the, sorry, that's green. I should have said green throughout. And when drawing the red boxes, the user is excluding those trajectories that go through those red boxes. So you can look for trajectories of the stone that pass through certain regions and miss other regions. And here's another example where this sort of idea can help you to find physical but very implausible trajectories of a person falling downstairs. So here's a person falling downstairs, and most of the trajectories you see here are taking the person completely off the side of the stairs. But sometimes you have these unlikely scenarios where you can have these unlikely scenarios where the leg gets caught. And so if one of the trajectories happens to find the one where the leg gets caught, the Google search essentially allows you to hone in on that interesting trajectory. So by having the hardware just compute lots of possible trajectories and then honing in on the ones you're interested in, that's one possibility. Another thing that you might do is you might go parallel, but not in the hardware, but in the software. That is, go parallel in a human sense. So not computer software, but people software. And there's been a bunch of interesting experiments in doing this, and one of my favorites is the Foldit project. So protein folding is extremely hard. The idea is you have some protein and you want to know what, you have the formula for it and you want to know what shape does it actually take. And even supercomputers cannot solve this problem. So the idea is maybe if we have many people working on it, we can solve this problem. So there's some work from the University of Washington where you can basically go online and you can download this game. It's a really fun game. It's called Foldit. And let me see, there should be sound here. Well, we're not going to get the sound, but I basically, oh, there is the sound. So as I go through these levels, I'm actually playing with this and trying to fold the protein, and I get feedback. This is just a very simple tutorial level. And it's really entertaining. And so you have tens of thousands of kids all over the world that are folding these proteins, and the computer is giving them feedback on how they're doing. So that's another way to go parallel. I need to get rid of this for a second. So that's just strategy number one, is go parallel. Strategy number two is to say, well, maybe we can make some more intelligent decisions as we explore this design space. So lubricate the design loop. What do I mean by that? If you think of a typical design loop as saying you have some idea, you try it out, you either build it, you build a little mock-up of it, you evaluate it, you get a crit, and then you go through and revise it and make new ideas. If we can speed this up somehow, so of course we're used to the idea that a computer can replace some of the building. We can do previs, we can do some renderings, we can see how things will look. Maybe that can save us time. But can we get this loop to be really fast? Can we really get it to the point where we eliminate the distinction between all these stages and it gets to be really fluid? I think the way I kind of think about it is interaction builds intuition. If I gave you one of these little puzzles that you have to pull apart, and I said, stare at this for 2 hours, just in your head, just looking at it, then pick it up and solve it. Or if I gave you 5 minutes, but you could play with it, you'd have a better chance if you played with it for 5 minutes than if you stared at it for 2 hours and then made one attempt at it. So really interacting with the system builds a lot of intuition. So this is a mock-up of a project at Carnegie Mellon called Claytronics, where the idea is if you had a holographic display, if you had actual physical tiny little robots that assembled together and that you could edit, then you could really work through a very quick process with many people interacting at the same time. I want to show you not physical versions of that. I think I only have like 3 minutes left. Is that right? More or less. So I'm going to skip this. I'll go back to that if I have time. Okay, so here's some work by Nobuyuki Umetani, who is visiting our group from Tokyo University. He's here for the next year. And Nobuyuki is interested in kind of blurring this design loop in the sense of when you're interested in finite elements or physical construction. So what you're seeing here is that as this shape is edited, which is just a constructed shape before any physics are applied, you're seeing at the same time what this shape does when you have gravity acting on it. So you immediately get as you edit the actual material, you're seeing instant feedback on what happens to the deformed shape under gravity. So this can give an engineer a lot of intuition about what's going on. Now, I also want you to look at this and say, this is a really neat idea. This is the state of the art. And this is a very, very simple mesh in 2 dimensions. So we're really far out from being able to do this for a complex model at interactive rates. But already this shows you the sort of power of having the stuff be very interactive from the get-go. Here's a vibration analysis. So this platform is vibrating. What the user is editing in real time is the shape of this box or the height of this box or placing windows or holes in it. And they're immediately seeing interactively, as they edit this, how the shape is vibrating. This can help build intuition, presumably in the long run, for things like understanding how different shapes behave under earthquakes. Similar examples for wind tunnels and vortex fields. So this is a fluid simulation, so you're kind of getting the trace of all the smoke going through this wind tunnel as you put different obstacles in the way. Again, a very powerful idea to be able to do this interactively, still in very much the primitive stages. And I think this is a really fun application because I love tea. So here, you're seeing a fluid simulation, and what you're seeing is editing of the shape of the teapot. And if you had some understanding of how you'd like the convection to circulate nicely in there, then as you design this product, you would get immediate feedback on how the shapes. And I think that, again, by playing with this interactively, you can get a real feel for what's going on. Example, this one is in the area of sounds. For a very, very simple scenario, you have a little now you're trying to design a wall. And the system is giving you, it's interactively running a sound simulation and giving you feedback on how loud things sound as you change the height or shape of the wall. The system could presumably also show you the cost of the wall and building time and other things. So the idea is, strategy number 2 is, if you can interact with the design system in real time, you can get an intuitive feel for what's going on. So that's what I was just thinking are 2 of the possible strategies and some of the, just give you a sense of some of the state of the art in those technologies. And of course, I've been showing you work by a bunch of different people. I thank you very much.
Our last speaker tonight is Miko Matsumura. Miko currently works at Servo, but until very recently he was vice president and chief strategist at Software AG, which is the largest independent provider of business infrastructure software. Miko is a thought leader in the areas of cloud computing, interoperability, and service-oriented architecture, SOA. In fact, Miko literally wrote the book, SOA Adoption for Dummies. Miko was also last year named one of the world's 30 most influential virtualization bloggers. Prior to his work with SOA, Miko was chief Java evangelist at Sun Microsystems, and he has raised countless millions of dollars for software startups. Miko holds an MBA from San Francisco State and a master's degree in neuroscience from Yale. Thanks, Miko.
Great, very much appreciated. So I'm very excited to be here, and thanks very much for the hosts and for all of your valuable non-refundable time, so thank you very much. I feel a great onus. I'm also amazed to be following these speakers, quite an astonishing array of intellectual power. So I feel it is my duty to create a absolutely beautiful, intact synthesis of everything that you've seen and tie a bow around it. But unfortunately, I believe that I'm destined to fail in this effort. We're moving into this notion of post-parametric era, and the thing that this evokes is it evokes another post that comes from the architectural realm, which is that of postmodernism. So right around the fin de siècle, we saw this wonderful poem that was evoked by Makai when he was talking about the centrifuge. Right, which is this construct of the widening gyre, right, this sort of descent into the center not being able to hold. And of course, this is the tissue of modernity being completely rent. And of course, the center ultimately did not hold, and we experienced the breakdown of the dominant meta-narrative, which eventually resulted in the destruction of this whole cloth sense of meaning in the world. And subsequently reduced human endeavor into a squabble for power in the ruins of the dominant meta-narrative. Okay, so much for beautiful synthesis. Okay, so that's pretty grim. So what I thought I would do, I thought I would counterpoint Eitan's very optimistic speech. One of the things that's clearly true is, you know, when you come from a provider of business infrastructure, you begin to realize the fundamental limits of scale end up being the human factors themselves, right? So the thing that is very interesting, I had lunch with an old friend of mine, and he is an architect. And he's actually struggling not with post-parametric, but he's struggling with parametric, which is his firm is shifting from AutoCAD into Revit. And he feels like he's old and over the hill, and all these young kids coming, you know, out of Columbia know all this great software. And, you know, it's almost like he feels like he's clinging by his fingernails to this immense ball of complexity. Because what emerges in this kind of paradigm of software development, so I, you know, until recently worked for a $1.5 billion software company, is that the software companies evolve with the buyers, not the users. So they really design their software towards RFIs and RFPs where you have billions of checkboxes of features, and at which point the user ends up in this staggering ball of complexity, right? Because essentially what's happened is that in the sort of domain of the kind of Henrik Ibsen master builder paradigm, essentially this piece of software is attempting to swallow the universe of complexity, and it's, you know, only one piece of software. So this is a huge challenge because really you don't want to experience this sort of degeneration or descent into horrifying complexity as you start to manage these extremely densely interconnected variables. Because in the emergent field, not only is the architect functioning much like the Ayn Rand character in The Fountainhead, Howard Rourke, the magnificent, bold individualist in a sea of sort of rampant collectivism, right? So, you know, this is one vision for architecture, obviously not the dominant vision at this time. But the concern is essentially that the architect is not operating in a silo of architecture, but in fact is integrated into a holistic system with people who actually construct and manufacture designs and who in fact are part of this entire so-called commercial supply chain of space creation, right? So in any case, brings me to a quick question, which is, what does architecture look like 10 years from now? So, you know, I'll say it right away. I have no idea. But what I'd like to do is take a few buzzwords. So I think clearly it will be distributed, and it will be approachable by scale, by massive scale, whether it is computational scale or the scale of the problems that are faced. So, you know, New York is a pretty big city, but if you look at a place like Sao Paulo, Brazil, 22 million, Tokyo, 35 million population, one of the exponential factors of growth in scale is human population. So we'll be dealing with really interesting issues around architectural design scale, but also this construct of externality, things like pollution, things like regulation. So the design environment becomes extremely multidimensional and heterogeneous and has thousands of different externalized constraints interoperating against the design, right? Rampant collectivism indeed. So perhaps a scary environment. Integrated, so it will be an integrated architectural model. I think integrated is important in the sense that one person's tools will be integrated with other different people's tools that have different jobs and different job descriptions. It will be interactive and real-time, potentially even kinetic and intuitive, right? Which is really critical, which is that the design of these systems must achieve a level of simplicity and intuitiveness for each type of user. Now, we could also envision a design environment which is smart and exploratory. So these are all really wonderful aspirations. But unfortunately, the scope of my talk is actually pointed in a slightly different direction, which is I'm here to actually talk about the cloud. So I'll try to compress that into the remaining minutes I have, because the question becomes, you know, does the cloud hold out the promise of helping us achieve some of these design goals for the architect of the future? So I believe that what we have here is a wonderful example of Occam's razor, which is, I talked about exponential functions creating challenge like population, But one of the things that's driving our world is the exponentiality of technology and emergence. Now, if you look at cloud, I'm going to tell you what cloud is in a moment, but it really is infrastructure. And if you think about it as infrastructure, it's boring, right? I mean, pavement is infrastructure also. We don't think a lot about pavement. We don't spend a lot of time thinking about it. Now, is the pavement changing exponentially? Maybe not. So another thing to consider is, other than the extreme boringness of infrastructure, is infrastructure at its best is invisible or close to invisible. And we only notice infrastructure when it's not working well, right? So the compute infrastructure is undergoing exponential change, and that's one of the principles of what this Occam's razor concept, which is, you know, we have big problems that are driven by exponential growth of things like population. And we have exponential growth of technology, so Occam's razor says, well, let's just smash these two together and see what happens. Maybe something good, right? So perhaps not the best amount of reasoning, but it's a decent idea. Because human beings are really bad at understanding exponential functions. So that means it's a fun area to think about. Moore's law, of course, everybody knows, every 18 months, bang, doubling of transistors on a die for the same cost. There are other laws, Gilder's law, Metcalfe's law, that cover the doubling of bandwidth, of network value. There's a RAM doubling law, there's a storage doubling law. These are all doubling. The thing that is fundamentally not doubling is human beings' ability to work and play well with others. So in my job, so I recently put my money where my mouth is and recently joined a company called Servo, which is a $0 billion startup focused entirely on constructing a mobile data cloud. So that's my fascination with the cloud, but in my work at Software IG, I worked on integration software to glue together parts of banks and governments and big, big institutions. So this got me involved in service-oriented architecture, and that's where some of my background comes from. So infrastructure changes are hard to understand. So here's a quote from the British Parliamentary Committee that studied electric lighting. They essentially said, electric lighting is good enough for our transatlantic friends, but unworthy of the attention of practical or scientific men. Right? Very, very dismissive. This whole electric light bulb thing, it's a fad. We just have to sit tight. Why? Why does a person think this way? Here's why they think this way. It's very simple. It's very simple. Because there's already an infrastructural mechanism for delivering light. It's the gas lighting system, which was ubiquitous. So the concept that you would change such a thing is almost insurmountable. But in fact, change does happen. So, I guess what I wanted to talk about is scalability, which is, I think, people have been accustomed to the principle of scalability as being Moore's law, which is we are limited by the availability of compute. And in fact, the thing that's funny is I mean, you know, I'm a dad, so you watch your kid. If there is some limit, then that's all that gets focused on. So a kid will look at that limit and say, as soon as this barrier is lifted, my life will be perfect. And computer people have thought that as soon as you get as much compute as we need, life will be perfect. That isn't the main problem of scalability. So, cloud. So what is cloud? It's this very large paragraph. This is the National Institute of Standards and Technology's definition, and probably the most ubiquitously agreed upon definition for cloud computing. Essentially, it suggests a utility model, paying per usage, and it allows a shared pool of compute resources to be rapidly provisioned and deprovisioned with very little interaction. So it basically means, like an electric grid, you pay for what you use. If you use a lot, boom, you have a lot. If you use a little, boom, you have a little. It's not that weird of an idea. Comes with these characteristics, models, and deployments. So the 5 key characteristics are on-demand and self-service, ubiquitous network access, which means you can get to it on your cell phone or whatever, location-independent resource pooling, that means no matter where you are, you can get to stuff, rapid elasticity, which just means that it scales up and down whenever you want, and pay per use. Those are the 5 key characteristics. 3 delivery models are infrastructure as a service, so Amazon Compute Cloud, platform as a service, things like Microsoft Azure or Google App Engine, and things like software as a service, things like Salesforce.com, Google Mail, Gmail, Google Docs, anything that's delivered as a service this way. So those are the delivery models. And then finally, 4 deployment models. One is called private cloud, where you as one entity own every single piece of hardware. There's some debate as to whether that's quote unquote a real cloud or not. Community cloud, where multiple organizations share a single resource that's distributed this way. Public cloud, which is the most common and ubiquitous cloud concept, so something like Google public cloud. And then hybrid, which is any combination of public and private clouds. So those are the 4 deployment models. So the goal is to go from the very small all the way out to the very big, right? So scalability. So the thing that I wanted to get across to you is that scalability is not compute constrained for long. It may be compute constrained now, but it will not be for long. And so what it comes down to is, what are the fundamental limitations of scalability in the cloud era? So I think one of them is you pay attention to interfaces, right? So one interface that's fundamental to computing is the concept of a computer. So the computer under this guy's desk is just an interface, and in the cloud paradigm, it is an interface to a distributed network of potentially extremely large numbers of virtual machines, but that the parallelism and scalability is automatically managed. So the machine is just a metaphor, but it makes it very easy to program. It's very hard to program a million arbitrary machines. It's very easy to program the one machine under your desk. So it goes from personal computing to universal computing. So from personal experience, this is the #1 website in Seattle, which is called Cheeseburger Network, to universal experience, the scalability of systems constrained by the amount of fun that people have with it. And finally, I just want to talk about an example, and I don't have very much time, but there's basically a group startup called SmugMug, and they've created a cloud system called Skynet, and it's basically a set of autonomic workers that sit in the Amazon Elastic Compute Cloud. So as more tasks come into the network, if 10,000 users suddenly decide they want to do web-based photo editing, which is what they provide, they're going to autonomically generate additional virtual machines in the compute cloud. Very exciting activity. It is 0.5 petabyte of data, and it is a profitable model for business. So this is basically what happened, which is you start to see utilization versus provisioning. And as you can see, it's dynamic, right? So more and more virtual machines are spawned as more and more workload is put onto Skynet. So that's basically a model for that elastic computation. So the note that I kind of wanted to close on is this build out of this construct of the software metropolis, which is, I've said repeatedly that the compute model is not the limit to scalability. The limit to scalability is essentially the integration not of data, the integration not even of semantics or meaning, but the integration of intentionality, which is that different groups of people naturally form Robin Dunbar number size tribes of 150 people. They form these tribal organizations that naturally combat one another, and they fight for budget and they fight for headcount. This is the nature of large organization. Therefore, the limits are trustworthiness, common languages, the ability to manage relationships, contracts and accountability, complexity. So I talked about some of these design systems achieving horrifying levels of complexity. That needs to be managed. Understanding. How do you even communicate that level of complexity to someone. Chaos and controllability and scalability of organization. So these are some of the fundamental limits that we need to overcome in order to achieve extreme large-scale systems in the cloud. Thank you very much. I think we're just going to come over here. Okay.
To ask some questions, help us speculate on what we just saw, try to make some meaning of all of this. So I'll just make a quick observation, but very quickly we want to open the floor to a few questions, and we'll probably try to wrap up in about 15 minutes. So one of the things that I just wanted to note, maybe it goes without saying, but the aesthetic of the graphic presentations in the room tonight was probably different than anything we've ever seen, at least in a row in this room, and I think that's interesting. I don't know if that's a certain message for the aesthetics of the post-parametric, but certainly it suggests a certain kind of conceptual and maybe even language issue in trying to think about the way that architects and computer scientists, we're talking very broadly now by saying that everyone here is a computer scientist, but that there's some issues of kind of communicating and finding graphic language, and I certainly think that the graphics were as compelling as the things that we do in architecture, but it's actually not exactly what we might have dreamed up if we all collectively as architects thought about what would the post-parametric future look like. With that as a kind of observation, I think it wouldn't necessarily make sense to try to summarize or make some great conclusion about all of this stuff, but I did want to bring us back to the idea of collaboration between fields, and particularly about innovation. You know, at a school like this, we're always thinking about innovation, thinking about new definitions of things, thinking about breakthroughs. And so the question I wanted to pose to anyone who presented who might want to answer is, are there examples, or I'll put it this way, how do you design the problems that you set out to solve with your tools and technologies? Like how do you come up with the idea of trying to design a robot that can repair itself or be self-aware? How do we come up with the idea to model a building that can that within the software you can interact with in real time, or even Miko? How do you come up with the problem of the software to design that you think will be helpful? And as a kind of subtext for that, is there a way that you could imagine in your own work for architects as non-experts, almost by definition, helping to define those problems, to create some kind of feedback loop? Because it seems to me like one of the issues might be that architects as non-experts asking a lot of stupid questions about these innovative processes might just seem to be in the way.
I'd like to take a crack, even though it's a bit orthogonal, which is one of the things I talked about was the system of production of software, right? So when you look at a very large company like, Autodesk and something like Revit, like there's so many inputs, but that ultimately the goal is to get large purchase orders. So they're not actually designing the system for use by humans, and that they're cramming features. And this is creating this kind of really horrible kind of interfaces. The interfaces are very, very complicated and scary. They're terrifying. And so the thing that's interesting about the innovation cycle in the cloud is that the cloud kind of fosters an economic model where you can actually build software at an individual level. It may not be you yourself as an architect, but it may be a single programmer building something in the cloud, and that you can actually start to network these very small and potentially very intuitive tools. It's along the lines of what Eitan was showing. So, I think that a network of much more simplistic tools may actually have a multiplying effect in the cloud. And the economic model for that is actually iterative and, you know, potentially exponentially growing if it catches on. So that's my pitch to you is ditch the big monolithic corporate architecture tools.
Maybe put on my my previous career hat as a developer of software for visual effects studios. I think there's, and I imagine it's very similar in architecture. So I spent a lot of time working with artists directly. And yeah, the languages that people speak are completely unrelated. I mean, it's a fascinating thing. And there's this role that in every visual effects studio, there's a fairly small group of people who can speak both languages, who act as these sort of translators. And I think they're the reason that visual effects has progressed at all, in many ways. And you know, where they come from is a good question, because I think they tend to be very diverse. So I'm thinking of people I've worked with who, I know some people who had art degrees and some people who had engineering degrees, but in every case they sort of developed the ability, the sensibility in both fields, and the ability to speak fluently in both languages and translate between them. And it's a very rare skill. But I would say from the perspective of, you know, trying to foster and practice collaboration between these communities, developing that skill and finding those people and figuring out how do you train people who can be conversant in both languages, I think is really key.
I can, there's one thing that's driving a lot of the work that we're doing, and that is the increased complexity of the kind of things we want to make. And I think this pervasive across many fields that involve design, is that you just want to make more complex things, and it's becoming too complicated for a single person to know and predict what's going to happen, and even for teams of engineers, let's say, to be able to understand the complexity of the things that we want to design. And that's compounded with the fact that the manufacturing tools now allow us to manufacture things with such great complexity that design space cannot be explored using traditional methods. And so a lot of the things that we've seen today, some of the things that you've shown, Eitan, have to do with accelerating the rate of exploration. What we're trying to do is have the machines explore themselves where to go next. So actually kind of take the designer out of the loop to some extent. But we're going to keep a switch
It's the last stage of optimization.
Yeah, right. We just want to be able to say, okay, what's the goal? And, you know, call me, text me when you get there. But it's all about reaching this higher complexity that cannot be managed using traditional design techniques, and that's what's driving.
So I just wanted to respond really quickly. So first of all, Hod, I was completely blown away by your presentation. I really loved seeing all of what you were doing, and I think that concept of having a gigantic multidimensional search space that that you can crawl or evolve towards, I think is great methodology. But one of the things that I see in sort of the enterprise domain, very large scale systems, is that it isn't complexity that's some of the problem that they have. Some of the problem that they have is entropy, which is that successful very large scale systems are kind of necessarily complex, and you have this wonderful kind of, like the biosphere, for example, tremendously complex, but relatively low entropy, right? Because it's actually taking solar energy and using it to build a diversity of form, right? And so the thing that's really intriguing to me that produces entropy within systems is that people bang against each other, and it's the heterogeneity of intention, right? I mean, I think that's really the kind of key puzzle that's unsolved. And I think in terms of manifesting very large-scale complex systems commercially, you will have lots of people working for lots of different entities that all kind of like want to win and push cost and complexity and entropy out of them and into other entities, which produces risk.
Should we open it up to some questions from the floor? Please go ahead.
Along those lines, what are some ways that enable dependencies to be working in parallel?
Yeah, so the big pattern that we looked at in service-oriented architecture is this concept of externalizing essentially policy. And so this concept, the pattern, and I apologize for not translating it to architectural constructs, but essentially what you do is you create trust by building a framework. So I'll give you an example. When people drive on the roads, they don't have an explicit point-to-point trust relationship with every other driver on the road, right? They have a trust in the framework, right? And so what you do is you devise frameworks, and then you create enforceability, and then that way what happens is the integration of these different intentionalities, right? So I plan to do X, other person plans to do Y. We have some kind of like legislation or some kind of construct that allows these things to cooperate. So for example, it's like, sure, you can have the air volume in this building be a certain size, but if it exceeds a certain size, then all of a sudden some environmental regulation from the government clicks in, or so how do you get these different, very wrong metaphor, but the construct is the same, which is how do you get these different intentionalities and constraint systems to interlock? And if you could get them to interlock in a model that had intuitive interaction to it, it would be even better.
I'm going to add something there about redundancy, and I think Jonathan can speak a little bit more to that, but whenever you take the approach of saying, let's go parallel and let's try to evaluate many, many different designs at the same time. So whenever you have a parallel system, actually reaping the benefits of the parallelism is really hard, right? And you rarely reap 100% of the parallelism. So if you have 100 explorations at the same time, you're not going to get 100 times the speed. But a very interesting anecdote for that is when you have humans in the loop. So with Foldit, the protein folding project, one of the things that the creators of Foldit discovered is that even though there were, so many ways to fold a protein, and that's ultimately what overwhelmed the computer, even the fastest computer that's trying to fold a protein, is that people, even in the thousands, started doing very similar things, all right? In part because they gravitated towards the same things on their own, and in part because all these bulletin board and forums opened up where people were sharing strategies with each other for how to get more points in Foldit, because that's what they're after, is getting the points and being highly ranked for their protein. And so that led to a very interesting problem, which they're working on right now at the University of Washington, which is how do we create incentive structures in these programs, in these games like Foldit, to encourage people to branch out and think outside the box and try different things, right? So how can we reward people for behaving differently from other people in this game, and therefore exploring different designs, even if those designs initially aren't as promising as the tried and true methods?
That's fantastic.
Thank you. Mark?
I want to ask a question about this word intuition, and maybe an analog we can make between intuition and computer science is also actually the word naive, right? Sometimes you hear this in computer science demonstrations where people will say, for instance, well, the naive way of doing this would be, and then they'll say something that seems totally reasonable, right? Like, of course, that's how something works, and that's the intuitive understanding of it, right? But then they'll say, but clearly this is a better way to do it, right? And they'll say some kind of bizarre optimization that some genius had to invent, right? And computer science seems to be the accumulation of all these optimizations, which is what makes it really hard to, number one, learn. Also somewhat hard to teach, right? But it also just moves it away from that sense of being intuitive. And I guess my question is, once we pass that real-time barrier, and once we start to have this completely elastic cloud that totally takes off the compute limit, as you say, is there a space then for naivety again? Can we be naive in the cloud? Or do we still have to do all the optimization?
I'm going to leave it to whichever you gets the mic first, because there are a lot of
I'll just say
potential
one
answers
thing.
to this.
We definitely have to rethink what are the notions of naive. And many computer science programs in the US right now are rethinking basic education of computer science with parallelism in mind. So what used to be a task that, was an n-squared task, meaning that if you doubled the size of the problem, it would take you 4 times as long, if you quadrupled the size of the problem, it would take you 16 times as long, suddenly can become a linear task in parallel with parallelism. And so some of the notions of what is obvious and what you should do and shouldn't do are certainly changing even at the curriculum level in computer science.
I guess I'd like to respond by saying that that's a kind of a very computery sciencey answer. I think, you know, my crack at this thing.
Definitely is.
Yeah, my crack at this thing is that the joy of what's happening with cloud is abstraction, right? So this concept of cloud, you notice infrastructure as a service, software as a service, right? Platform as a service, everything's a service. So what is a service? A service is basically, I don't care how it gets done. You do it and you deliver it and I'm not even looking at you, right? That's what a service is, right? And so what that means is that kind of abstraction I was talking about programming a computer. So I'm programming a computer. That's simpler than programming a gigantic network of computers, right? And so what I'm really trying to say is with boundless compute capability, I think your hypothesis is true, which is that with a lot of compute power, we can present abstractions that are very, very simple, but in fact are underlying. There's a lot of complexity inside of it, and that it's doing the work to give you a very simple interface, right? So I think it's possible, but I think it comes back to the means of production of software, which is, you know, that if you give people an economic reason to build hideously complex pieces of software, they'll do that, right? So that's, I think, what the closer to the issue.
I think another aspect of that is computer science is difficult. It's a difficult engineering field, and like all engineering fields, the engineering trade-offs are the hard part, and they're almost always unintuitive. So in defense of computer science, I don't think it's any worse, right? Like, generally what makes engineering a hard discipline is that the easy answers tend to not be the best answers, right? So the advantage of more and more powerful computers is that you can actually hide all of that complexity. The computer can do the hard work of figuring out what's the optimal answer, what's the consequence if you put in these parameters, what do you get at the other end? Or it can let you be intentional and say, here's what I'm intending. You tell me where in the design space will give me that answer. I don't know where it is. Or, you know, what Eitan and I were showing, the idea that you can have a really difficult the path from input parameters to output result can be, you know, really, really complicated sequence of computations. But, you know, if that's interactive, then you're sort of directly, it almost feels like you're directly driving the output, right? Instead of this sort of process or input, wait an hour to get output. And so I think as computers actually get faster and faster, the intuition of these complex systems actually increases, because you can actually develop the intuition directly by playing with the system itself. So I think it's actually hopeful as computers get faster and more complicated for the naive users to actually use complicated systems to do interesting things.
Let's take one more question and then we'll have to wrap up. Way in the back row, highest hand.
Okay. Great lecture by the whole panel. So back here, we've been kind of wondering. There's like a kind of underlying theme of utopia and dystopia in a way, right? Like there's an image of Skynet, right? A company actually makes a company called Skynet, and with like a real kind of quote about possible futures. And I guess we're all wondering that it seems like there's an end goal to some of and in different fields there seems to be like an end goal, like in at least in graphics, right? The end goal would be reality to some degree, right? That we're going to completely be able to simulate reality. In robotics, it might be the autonomy of a robot, right? It might be autonomy is the end goal. And I guess we're wondering here, like, is that something that's conscious to the minds of people within those fields, like the kind of consequences of that? And I don't know. I mean, it's not that we're scared. I mean, there's a kind of like promise to everything, but at the same time, there's a kind of like, we've seen so many scenarios that play out in very bad ways, and I'm not like I'm not a conspiracy theorist. I mean, you know, I'm extremely hopeful about it, but at the same time, like, I'll show my dad a video of a TED Talk, and he'll be like, where is this, like, you know, he's not up to date with technology, but he'll just be like, where is it going? You know, where does it end, in a way? So I was wondering, like, what are the goals, I guess? What are the end goals? Is it even seen in the profession or in the fields?
So, right, the question seems to be, is tomorrow going to be wonderful with all our needs fulfilled and wonderful robotic doctors, or is it going to be the you know, day-to-day fight for life against humanoid robot killers?
Children of men.
I can try to speak for robotics.
As a designer of hunter killers.
But so I think the direction is autonomy, but the end goal is not clear because we don't know what you know, how much autonomy, what kind of intelligence, all these things. So it's not clear where it's going. It's probably, but we want to get more autonomy, and I think that it's. I used to think, you know, you don't need to worry about it. Go worry about genetically modified crops or something else, but not about robotics because you can unplug them. But the truth is, it is a powerful technology, and I think the only way to deal with it is to have public discussions just like we're having here. You know, here's what we're doing. It looks cool. There's probably more benefits than harm in the potential, but let's just keep it open and see where it goes because nobody knows where it's going.
Let me just follow up with a quick comment, which is, you know, what it suggests and your comment suggests is that we're actually still not necessarily in post-parametric, but we may actually be in postmodern, right? Which is that, you know, one of the things we need to really study is whose intention is served, right? Because ultimately, these entities in their behaviors project an intentionality. So if you're looking in a design space, you could look in a design space of what's the most efficient way to create a green building. That's an interesting design space. What's the most cost-effective way to kill 50 million people, right? That's a different design space. Horrible dystopia design space, right? But the thing that I think ultimately have to consider is whose intentions are being extended and how do these systems serve those intentions? And I think your question is extremely thoughtful because, you know, everyone needs to examine those questions.
Yeah, I too really appreciate the question because it indicates the kind of moving from the means to the ends, and I think that the notion of post-parametric in a way is like a relief to me because we might actually get back to the business of creating kind of sublime human experience of space, or the kind of things that have constituted, you know, the architectural education and design practice for so long that seems to have gotten really pushed down under encountering tools. So I'm kind of looking forward to getting back to business in a way.
And I think that's a good way to wrap up. This is obviously just the beginning of a discussion. But I want to thank all of our speakers. I want to thank our sponsors, Columbia Department of Computer Science, Blue Sky Studios, and Bentley Systems Incorporated. And I want to thank everyone in the audience for being willing to bend your mind in multiple directions at once. So hopefully this is to be continued. Thank you.